Part 5, EPA and DHA through the SBM lens. Chapter 14, EPA-derived Resolvins E-series. EPA-derived resolvins, often grouped as the E-series, are one of the clearest examples of how omega-3 becomes biologically important only when it is understood as precursor material for phase transition rather than as a generic anti-inflammatory input. EPA by itself is not the resolution event. EPA is the stored substrate from which a family of later phase signals can be generated once the tissue has moved far enough beyond initiation that continued escalation is no longer the correct priority. E-series resolvins matter because they help the body change the instructions governing an inflamed site. They reduce the continuation of neutrophil-heavy recruitment, alter the inflammatory environment away from repeated expansion, and support the shift toward cleanup, containment, and restored control. In that sense, EPA-derived resolvins are not merely softer inflammatory molecules. They are part of the body's machinery for deciding that enough acute force has already been used. The distinction between EPA and the E-series it can generate is critical because it keeps the biology from collapsing into supplement language. A person can consume EPA and still fail to produce strong resolution behavior if EPA is not incorporated meaningfully into membrane phospholipids, if the releasable pool remains too small, if enzymatic competition from arachidonic acid-heavy substrate remains too strong, or if the tissue never enters the phase in which pro-resolving mediator generation is supposed to take command. But when EPA is meaningfully incorporated and the tissue does transition, the E-series provides one of the main downstream routes by which omega-3 begins to exert true resolution influence. This is why the earlier chapters emphasized precursor logic so heavily. EPA is not the finished answer. The E-series is one of the ways the body turns EPA into an answer. One of the most important actions of E-series resolvins is the reduction of further neutrophil recruitment. This matters because neutrophils are useful at the beginning and expensive after that. Their continued arrival brings oxidants, proteases, membrane injury, endothelial disruption, and an increased burden of apoptotic cells that must later be cleared. A tissue cannot resolve while it is still being continuously restocked with acute phase machinery. E-series resolvins help interrupt that continuation. They reduce the conditions that keep inviting more neutrophils into a site that no longer benefits from their presence. In practice, this means the tissue begins to move away from active reinforcement and toward controlled drawdown. That is one of the most practical meanings of EPA-derived resolution. The site is no longer asking for more force. It is beginning to ask for less interference. The E-series also helps shift macrophage behavior in the direction of cleanup rather than continued inflammatory participation. This is essential because inflammation cannot end simply by stopping new recruitment. The tissue must also remove the remains of the inflammatory event that has already occurred. Macrophages have to become better at engulfing apoptotic neutrophils and processing debris before those materials become fresh inflammatory stimulus. EPA-derived resolvins contribute to that handoff. They support the transition from an environment dominated by arrival and amplification into one dominated by clearance and closure. In this way, the E-series does not merely restrain inflammation. It helps make the site more finishable. Another reason the E-series matters is that it changes the character of lipid mediator output without requiring the body to abandon inflammatory competence. EPA competes within the same broad biochemical landscape that otherwise heavily processes arachidonic acid, which means EPA-derived pathways can alter what kinds of signals become available when phospholipids release fatty acids from membrane. This is important because the body does not need less signaling in the abstract. It needs different signaling once the acute phase has done enough. The E-series helps provide that difference. It does not erase the logic of host defense. It changes what the tissue is being told to do after host defense has already been launched. This also explains why EPA-derived resolvins are especially relevant in tissues caught in chronic low-grade inflammatory repetition. Many such tissues do not lack activation signals. They are saturated with them. What they lack is enough later-phase biochemical influence to stop the repeated renewal of early-phase recruitment and vascular openness. The E-series becomes important here because it contributes to the molecular pressure required to shift the site away from perpetual reinforcement. A tissue with access to EPA-derived resolvins is better equipped to reduce further inflammatory traffic, improve cleanup efficiency, and begin reclaiming structural order after an inflammatory event. A tissue poor in that capacity may still inflame vigorously while remaining weak in the chemistry needed to stand down. Seen clearly, Chapter 14 is not really about a niche lipid subclass. It is about one of the major ways the body turns stored EPA into the language of closure. The E-series helps stop the unnecessary continuation of inflammation without suppressing the useful fact of immune defense itself. It reduces new neutrophil entry, supports macrophage cleanup, changes the downstream mediator environment, and strengthens the shift from escalation into completion. EPA matters because it can become this. Without that downstream possibility, EPA remains just another membrane fatty acid. With it, EPA becomes part of the body's capacity to finish what inflammation began. Eicosapentaenoic acid pathways. Eicosapentaenoic acid enters physiology through several linked pathways, and its importance depends on how those pathways connect structure to later signaling rather than on EPA existing as an isolated molecule in circulation. Once absorbed, transported, and incorporated into membrane phospholipids, EPA becomes part of the cell's stored lipid environment. At that stage, it is already doing two things at once. It is altering membrane behavior by changing the local phospholipid composition, and it is becoming part of the releasable substrate pool that can later be mobilized during inflammatory activation. EPA, therefore, does not matter only because of what it can become downstream. It also matters because it changes the structural context from which downstream decisions will later be made. The first major EPA pathway is competitive incorporation into phospholipid membranes. This matters because EPA does not enter empty tissue. It enters membranes already carrying other fatty acids, especially omega-6 derived substrate that may already dominate inflammatory potential. If EPA incorporation becomes meaningful, it changes the future composition of the releasable pool. When phospholipids are activated during tissue stress, there's now a greater chance that EPA will be among the fatty acids released from membrane phospholipids rather than the site drawing almost exclusively from arachidonic acid-heavy stores. This is the first way EPA shifts inflammatory biology. It changes the reservoir before the event, which means it changes the probabilities during the event. The second major pathway is EPA entry into eicosanoid-producing systems. Once liberated from membranes, EPA can compete with arachidonic acid for cyclooxygenase and lipoxygenase processing. This does not remove inflammatory signaling from the system. It changes the chemical options available within that system. The tissue can now generate EPA-derived lipid mediators rather than relying only on arachidonic acid-derived products. That shift matters because the mediator field becomes less exclusively weighted toward the initiation-heavy language of prostaglandins, leukotrienes, thromboxanes, and related compounds produced from omega-6 dominant substrate. EPA therefore alters inflammatory output partly by changing what the enzyme systems are being asked to work on. Is not replacing signaling with silence. Is shifting signaling toward a different substrate base. The third pathway is the generation of E-series resolvins. This is where EPA becomes especially important in the context of resolution. Once EPA has been incorporated into phospholipids, released under the right conditions, and routed through the appropriate downstream enzymatic sequences, it can be converted into E-series specialized pro-resolving mediators. These molecules are part of the later inflammatory phase. They help reduce further neutrophil recruitment, improve the shift away from repeated amplification, and support the handoff toward macrophage-led cleanup and closure. This is why EPA should not be called merely anti-inflammatory. Its deeper significance is that it feeds a pathway capable of helping inflammation finish rather than simply continue under a slightly weaker form. EPA pathways also matter because they operate inside competition and timing, not in a vacuum. A person may increase EPA intake and still see only partial downstream effect if arachidonic acid-heavy substrate remains dominant in membranes, if COX and LOX pathways remain crowded by early-phase inflammatory traffic, or if the tissue never truly enters the stage where mediator class switching toward resolution can take command. This makes EPA biology nonlinear. Small increases in intake may produce little visible change at first. Then, once membrane incorporation rises enough or inflammatory burden shifts enough, the same EPA presence can begin exerting much stronger downstream effects because the pathway has crossed from theoretical availability into functional influence. There is also a structural protective dimension to EPA pathways. EPA is less unsaturated than DHA, which means it participates somewhat differently in membrane behavior and oxidative vulnerability, but it is still a highly unsaturated fatty acid, and therefore still requires a tissue environment capable of preserving it. If oxidative stress remains high, if membranes are repeatedly injured, or if mitochondrial dysfunction keeps tissues chemically unstable, EPA may be present without being fully preserved as clean substrate for orderly downstream conversion. In that case, the EPA pathway is not absent, but it is compromised. The tissue carries some of the precursor, yet remains too unstable to route it efficiently into strong pro-resolving output. Seen clearly, eicosapentaenoic acid pathways begin with incorporation, continue through substrate competition, extend into altered eicosanoid production, and culminate most meaningfully in the generation of E-series resolvins. EPA changes membranes first, signaling options second, and inflammatory sequencing third. Is not a terminal molecule with one fixed function. Is part of a pathway architecture that determines whether a tissue remains fluent only in escalation or gains stronger access to the chemistry of completion. Vascular and immune resolution. Vascular and immune resolution are inseparable because inflammation is never only a matter of immune cells entering tissue. It is also a matter of whether the vascular system continues behaving like an open emergency corridor or regains the selective control required for tissue to stop functioning as an inflammatory zone. Early inflammation deliberately alters blood vessels. Endothelial cells change adhesion behavior, permeability rises, local blood flow shifts, and the tissue becomes easier for neutrophils, monocytes, plasma proteins, and signaling molecules to enter. That is useful at the beginning because access is part of defense. But if vascular behavior remains locked in that state after the acute need has passed, the tissue cannot resolve. It stays too open, too exposed, too fluid shifted, and too available for repeated immune traffic. Vascular resolution, therefore, means the blood-facing surfaces of the tissue stop acting as if more recruitment is still needed. They begin closing the gate without trapping unresolved debris behind it. This matters because immune resolution cannot succeed while vascular permissiveness remains high. A tissue may begin generating some pro-resolving signals, but if endothelial surfaces still favor leukocyte adhesion and extravasation, fresh inflammatory cells keep arriving into an environment that should be transitioning into cleanup. The result is that clearance and re-entry overlap in a way that prevents completion. Specialized pro-resolving mediators help interrupt that pattern by changing both sides of the equation at once. On the immune side, they reduce continued neutrophil recruitment and improve macrophage-led cleanup. On the vascular side, they help shift the tissue away from emergency openness and toward tighter regulation of permeability, adhesion, and local inflammatory spread. This is what makes resolution a systems event rather than a single-cell event. The blood vessel has to stop supplying an acute phase environment at the same time the immune system stops demanding one. The vascular dimension is especially important because chronic inflammation often persists through microvascular disorder long after the original insult should have been contained. When endothelial behavior remains abnormal, tissue edema can persist, nutrient and oxygen handling become less stable, local inflammatory mediators spread more easily, and the mechanical environment of the tissue remains distorted. In that state, even good immune cleanup becomes harder because the site is still physically behaving like a place under active siege. Vascular resolution, therefore, is not just about less redness or less swelling. It is about restoring the physical terms under which tissue can return to orderly exchange rather than remaining a zone of exaggerated access and biochemical leakage. Immune resolution, on the other hand, means the inflammatory cell population changes jobs. Neutrophils stop arriving in excess. Existing neutrophils proceed toward apoptosis rather than prolonged destructive persistence. Macrophages shift from amplification and inflammatory participation toward erythrocytosis, debris clearance, and repair-compatible signaling. Cytokine tone changes. The tissue stops asking for reinforcement and starts processing the remains of what reinforcement already did. This is why vascular and immune resolution have to be synchronized. If the immune system shifts toward cleanup but the vessels stay open, new inflammatory cells continue entering. If the vessels begin tightening but immune cleanup remains poor, debris stays trapped and the site remains biochemically unfinished. Resolution requires that access and activity both be reprogrammed together. This is one of the clearest places where EPA-derived and broader Omega-3 derived mediator biology becomes meaningful. E-series resolvins and the wider SBM family do not merely soften inflammation in the abstract. They help change the operating logic of the vascular immune interface. They reduce the continuation of neutrophil trafficking, support macrophage function, and help the endothelial surface stop behaving like an inflammatory invitation. That combined effect is what makes tissue more capable of leaving the front half of inflammation behind. The body is no longer just producing fewer inflammatory signals. It is reorganizing who can enter, what they do when they arrive, and when the site is allowed to stop receiving more acute phase support. Seen clearly, vascular and immune resolution are two sides of the same closing movement. The immune system must stop escalating and start clearing. The vasculature must stop opening and start containing. Together, they convert an inflamed tissue from a place built for emergency traffic into a place built for restoration. Without that paired transition, inflammation remains partially open even when its visible intensity drops. With it, the body gains the ability to end defense without leaving the site unfinished. Inflammatory tone modulation. Inflammatory tone modulation refers to the body's ability to change the background intensity, sensitivity, and persistence of inflammatory signaling without simply switching immunity on or off. Tone is the right word because this is not about one isolated event. It is about the baseline pressure carried by the tissue before, during, and after specific triggers. A tissue with a high inflammatory tone is easier to activate, quicker to amplify, slower to calm, and more likely to interpret ordinary biological friction as meaningful threat. A tissue with a well-regulated inflammatory tone can still defend itself rapidly when needed, but it does not remain chemically tense when the threat is absent or already contained. Specialized pro-resolving mediators contribute to this modulation by changing the conditions that keep inflammatory intensity elevated beyond its useful phase. They do not abolish immune responsiveness. They lower the chronic background pressure that makes tissues feel primed for repeated escalation. This matters because chronic illness often involves not just discrete inflammatory episodes, but a persistent elevation in inflammatory readiness. Cytokine signals remain slightly elevated, endothelial surfaces remain slightly more adhesive, nociceptive pathways remain slightly more sensitized, macrophages remain slightly more biased toward inflammatory participation, and membranes remain slightly more loaded with the evidence of unresolved danger. None of these deviations may look dramatic in isolation, but together they create a tissue climate in which the threshold for fresh inflammatory activation drops. Tone modulation is therefore one of the most important functions of the resolution phase. The body is not only trying to stop one event, it is trying to reset the background conditions that would otherwise make the next event too easy to start. SBMs influence inflammatory tone by reducing continued neutrophil recruitment, improving macrophage cleanup, limiting collateral injury, and helping restore barrier and vascular control. Each of those actions lowers the amount of unresolved inflammatory residue a tissue carries forward. As that residue falls, the tissue stops presenting itself as chronically unfinished. Receptors encounter less damage-associated noise. Oxidized lipid fragments become less abundant. Endothelial surfaces stop behaving as though they must remain in open-access mode. Nociceptive systems lose some of the inflammatory evidence that justified sustained amplification. Tone falls not because the immune system has been weakened, but because the tissue has become less crowded with the biochemical reasons for continued alertness. This is one reason inflammatory tone modulation is different from anti-inflammatory suppression. Suppression can reduce visible inflammatory output while leaving the tissue structurally primed for rapid reactivation. Tone modulation changes the priming itself. It raises the threshold for inappropriate activation by helping remove the conditions that keep the tissue on edge. That is why it belongs so centrally to resolution biology. The healthier body is not the body that cannot inflame. It is the body that does not remain unnecessarily inflamed between genuine needs for defense. SBMs help create that state by reducing the background pressure of unresolved inflammation and restoring a tissue environment that no longer behaves as though emergency is its default setting. Cardiometabolic implications. The cardiometabolic implications of failed resolution are enormous because the cardiovascular system and the metabolic system are both built on membranes, vascular surfaces, immune surveillance, and fuel handling logic that are highly sensitive to inflammatory tone. When resolution works well, vascular tissue can mount a proportionate response to injury or stress, clear the resulting debris, restore endothelial control, and return to a lower noise state without remaining chronically reactive. Metabolic tissues can handle substrate flux, postprandial signaling, adipose expansion, mitochondrial demand, and immune traffic without becoming locked in defensive chemistry. When resolution fails, those same tissues begin living in a state of partial alarm. Endothelial surfaces remain more adhesive and more permeable than they should be. Immune cells continue trafficking into places where cleanup never fully finished. Oxidized lipids and damaged membrane fragments remain visible. Adipose tissue continues signaling distress. The liver remains biochemically crowded. Muscle and vascular tissues become less metabolically flexible. In that environment, the body does not simply have inflammation. It develops a chronic cardiometabolic pattern built from unresolved inflammation. The vascular side of this is especially important. Endothelium is not passive plumbing. It is a living membrane surface that constantly interprets shear stress, circulating lipids, glucose excursions, immune signals, and oxidative burden. A well-resolved vascular system maintains selective permeability, controlled leukocyte interaction, and a relatively quiet inflammatory baseline. A poorly resolved vascular system does the opposite. It remains easier for immune cells to adhere, easier for inflammatory signals to propagate, easier for oxidized lipid material to distort local behavior, and harder for the vessel wall to return to a truly resting state after repeated insults. This matters because the earliest stages of vascular dysfunction are often not dramatic obstructions, but persistent low-grade endothelial irritation, altered nitric oxide handling, abnormal permeability, and repeated immune engagement with the arterial wall. Resolution biology belongs here because the vessel must be able not only to react, but to stop reacting before temporary injury becomes chronic vascular remodeling. The metabolic side follows the same logic through different tissues. Adipose tissue is not merely a storage depot. It is an immune-active endocrine-active tissue whose inflammatory tone shapes systemic insulin sensitivity, lipolysis, hepatic fat handling, and broader cardiometabolic stability. When adipose tissue expands under conditions of poor mitochondrial handling, oxidative stress, and repeated inflammatory signaling, it begins recruiting immune cells and generating a biochemical environment more consistent with unresolved defense than with quiet storage. The liver then receives this burden through substrate overflow, inflammatory signaling, endotoxin exposure, and altered lipoprotein traffic. Skeletal muscle receives it through impaired insulin signaling, altered substrate competition, and lower metabolic flexibility. The vascular system receives it through endothelial stress and circulating inflammatory pressure. In each case, failed resolution turns ordinary fuel management into a chronic tissue-level inflammatory problem. That is why cardiometabolic dysfunction so often presents as a cluster. The same unresolved logic is being expressed across the tissues that handle flow, storage, transport, and oxidation. SPMs matter here because cardiometabolic disease is not only a problem of excess substrate, it is a problem of unresolved tissue response to that substrate. A body can handle large amounts of energy only if it can also maintain membrane order, preserve mitochondrial function, control inflammatory traffic, and clear the byproducts of metabolic stress before those byproducts become self-sustaining danger signals. EPA and DHA-derived pro-resolving mediators help support that later phase. They reduce continued neutrophil recruitment, improve macrophage cleanup, limit collateral tissue injury, and help endothelial and immune behavior shift away from chronic activation. In practical terms, this means better resolution biology may help reduce the persistence of vascular inflammation, adipose immune congestion, and liver-centered inflammatory burden that otherwise keep the entire cardiometabolic system in a half-defensive state. The issue is not that SPMs are a magic cure for metabolic disease. The issue is that without adequate resolution pressure, cardiometabolic tissues keep interpreting nutrient handling and tissue stress through the chemistry of incomplete defense. This is also where membrane composition becomes especially relevant. Cardiometabolic disease is often discussed through glucose, insulin, triglycerides, LDL, body fat, or liver enzymes, but beneath those markers sits the question of what kind of membranes these tissues are built from and what kind of inflammatory future those membranes make possible. A vascular surface built under omega-6 dominant, oxidatively unstable conditions is easier to irritate and harder to calm. A hepatocyte membrane built under chronic inflammatory load is easier to stress and harder to restore. Adipose tissue built under poor resolution conditions becomes better at recruiting immune participation than at returning to quiet storage. Muscle tissue under chronic inflammatory tone becomes less able to transition cleanly between fuels. In all of these cases, cardiometabolic dysfunction is partly the behavior of tissues whose membrane architecture has lowered their threshold for inflammatory persistence. Seen clearly, the cardiometabolic implications are not secondary consequences of inflammation. They are one of the main places unresolved inflammation becomes clinically visible. Endothelial dysfunction, insulin resistance, fatty liver, adipose inflammation, vascular stiffness, poor recovery from metabolic stress, abnormal postprandial responses, and chronic low-grade immune activation all make more sense when viewed as failures of closure rather than as isolated marker abnormalities. The body is still capable of responding to challenge, but is less capable of finishing that response and returning its metabolic and vascular tissues to low-noise function. That is why resolution biology belongs at the center of cardiometabolic thinking. A system that cannot complete inflammation will eventually struggle to handle fuel, flow, and tissue maintenance without turning each of them into a chronic source of danger signaling.